To get started with Hat OpenShift DataScience, you need to install the operator available in the operator hub. However, before you do that, it is recommended that you have some other operators pre-installed, since they are used by the Hat OpenShift DataScience functions, such as pipelines for Kubeflow pipelines and OpenShift Data Foundation for block storage, for S3 compatible block storage. Additionally, if you want to have MLflow running in collaboration with Hat OpenShift DataScience, you need to also install the Crunchy Postgres for Kubernetes operator, as it is described here in the prerequisites for MLflow. So let's head over to the operator hub and look for the data science operator. Click install, accept all the defaults, click install. This will take a while, so I will resume my recording once the operator is fully installed. The Red Hat OpenShift DataScience operator creates several namespaces during installation. One of the most important ones is Red Hat ODS applications. Here, under RHODS, you can have the access to the console. The first time you open the console, you will see this view depending on whether you are an administrator or a regular user. If you are an administrator, such as this user that I'm using now, you will also have access to the resources and settings area. For the settings, what you can do here is, for notebook images, import additional notebook images on top of the ones already available by default with the installation of the operator. You can also manage your cluster settings, such as the size of the disk that is allocated to a data science project, where the data scientist will store the files that is working with, whether to stop or not idle notebooks to save resources, allow or disallow collection of usage data, and add toleration to notebook POCs to allow them to be scheduled to tainted nodes. This function is particularly useful if you have nodes, machine sets in your OpenShift cluster that have GPU and some that don't. So in case you want your notebook to be scheduled to execute on a pod that has access to GPU resources, then the node should be tainted. Serving runtimes. These are the ones that allow you to serve your models. And then, of course, user management is the way that you assign rights and permissions to the users accessing the console. Next, to start, you need to create a data science project. So let's do that one in order to launch it. We are going to create the project test. You can add a description if you want. And when a data science project is created, several resources are available. The workbenches is basically where you create your Jupyter Lab instance. The cluster storage is where you add the cluster storage that is associated with the workbench. You can have several workbenches and cluster storage is added in the same project. However, one cluster storage can only be attached to one workbench at a time. Data connections are S3 compatible object stores, and pipelines are Kubeflow pipelines. For that, you will need to define a server. Models and model servers are the ones where you deploy your trained model in order to be used for inferencing. So the first step is to create a workbench. Here you can call it any way you want. There are by default several notebooks available. I will use a TensorFlow notebook. There are different versions, so I'll use the one that's recommended with a small container size. Environment variables, if defined here, they will be available inside the notebook right away. Since this is a first time I'm starting this project here, I will need to have a new persistent storage associated. So it is creating also at this step the storage that is associating it with the notebook image. Leave it at test. leave the defaults on. And now click Create Workbench. This will take a while because it needs to do some additional preparations in order to start your workbench, but it only takes a while the first time you run it. After that, starting and stopping the notebook will be much faster. Now our notebook image is running and we can have a look at it. So we see that there are several packages that have been created with this notebook image. If you need additional packages on top of this in order to avoid always doing a pip install whenever you launch your notebook, you can compile your own notebook images and import it here under notebook images as I previously shown. As you can see, also see the limits for this container, how they are being created. To access the notebook, just click on the link here and open. You're required to log in with your credentials. The first time it will ask you to allow the requested permissions. Now you have access to the Jupyter notebook. In order to use pipelines and the model mesh server, you need a data connection because it is where the pipelines will store any temporary files and the results of the execution, and the model mesh server will look for folders from where to deploy the models, to detect and deploy the models that are stored there. So let us define the data connection. Now, the data connections are available using the OpenShift Data Foundation operator. You can create a data connection directly in your test project that was created inside the data science project. So we called our project test. This created a new namespace in OpenShift, and we have one pod running here, which is our notebook pod. And you can create object bucket claims in here, like selecting the project and going there. However, if you installed ML Flow for experiment tracking, I recommend that you use that bucket and configure it inside the data science project. So in order to obtain the information from that bucket, you can click on the ML Flow project, and under object bucket claims, we will see the bucket information. You can click on it, and you have the information on how to connect to the bucket in this page. Now the endpoint here is not exactly the one that you need. It is the service endpoint from the OpenShift storage service name, and that is available here. So this will be the name that you need to use when creating the object store. Once you filled out the information about creating the object store, you can select to attach it to a workbench and then add the data connection. This will restart the workbench in order to make it available for it. Now that the data connection is available and created, we can define a pipeline server if you want to use Kubeflow pipelines, and definitely we want to add a model mesh server for deploying and serving our models. So let's create first the model mesh server. I'm going to call it test. You can select several runtimes that are available here, so we'll select the first one because this cluster doesn't have GPU. You can select how many replicas you want and the size. If you want to make the models available through an external route, accessible outside of the cluster, and if you want to require authentication for the requests. At the same time, we can create a pipeline. We can select the data connection, as I said it is required. We can leave the defaults on and just click configure. Please note that When you add the server, it is not actually deployed, it's just configured inside the uh, the model mesh controller. The pipeline server is deployed under your project. As you can see here, we have the instance for it and the database where the information is stored, but not the uh, model mesh server instance yet. That has just been configured. It will be created the actual instance when you deploy your first model. So now that we have our environment ready for work, let us start doing some data science. What I'm proposing to show you today is a project called Machine Learning Assisted System Performance and Capacity Planning, MLASP, using it on Red Hat OpenShift. The idea is here that we want to create a machine learning model that will help us define key performance indicators such as throughput in order to decide what configuration should be applied to a system in order to maintain that capacity. And the way that you can collect information and to use it in order to train the model, it is from collecting load test information about the test subject system. All the information on how to set up the system and the paper that is talking all about it, you can see it linked in here in this GitHub repository. And the instructions are provided step by step in order to set up everything that you need in order to recreate this demonstration. So now that I've imported the necessary files, I added also the missing packages because they were not available in the default notebook. And I already have a test dataset that I can use for modeling. So I'm going to run this notebook that will do the ML model. Now, there are two ways this model is being created here. One is in a sequential manner using the notebook server image and the resources it has available in order to uh, train the model. And this is done using this function over here. And for hyperparameter tuning, I am only tuning one parameter, which is the depth of the neural network in order to find the model that produces the best parameters. Of course, you can work with all the other parameters, but as this is for demonstration purposes only, I am using only the depth of the model. So I will run this function in 15 times to find out how long it takes to train in the notebook. Uh, then the second option is to actually use MLflow for experiment tracking and distributed computing with the array cluster that we created. So ensure that the URI for MLflow and array endpoint are exactly the one that you created in your notebook server. Now that the training has completed, let's have a look at the results. When we executed the training with Ray as a distributed training, the Ray get here, it is a blocking function, so it will wait until all the training is done. But it will also need to add extra time in order to get and compile the results. However, with all that, you see that the training and retrieval time for the distributed option, it took 58 seconds versus the 8 minutes and 2 seconds with the training within the same notebook image. And this is just by parallelizing the training of the uh, model with the hyperparameter tuning. Now, of course, the results that you may obtain when you run this notebook may differ based on the resources available to your cluster. In my case, the notebook image and the resources and the Ray cluster resources were defined in the same way. Once the training is complete, you can also visualize the results, so you can see how it performed. Uh, when you do it in the traditional way, you need to keep track of everything inside the notebook, right? So you need to get all your functions, need to make sure that how you store this data and everything. But when you do it with Ray uh, and with the MLflow to keep track of the experiments, you will see the results loaded in here. And one quick way to find out which model performed best is to select your experiments and then create a chart view and configure the chart, and to see what metrics do you want to see, and if you want to see also parameters, that's up to you, but we are only interested to see the model that performed best. So it's basically the one that has the lowest of the metrics that are the mean absolute error, the mean absolute percentage error, and the mean squared error, and the highest R2 score. So it's somewhere in between here, right? So it's 9 or 7 maybe. Yeah. So you can select one of these and have a look at how it performed. So by selecting this, you go to the details of the training, and you have information about the predictions stored already here. You have the model itself, and then we will use this information in order to deploy it. So we'll just copy this and go back to our model mesh and click deploy. We will call our model MLASP, select the framework. It's the ONNX one because it's compiled in this ONNX, existing data connection, and we'll put in the folder information, but we only need the folder information, top level folder information. So this is 7, and we don't need the model name. The trailing slash is important to add. So once again, this is the folder, right? So it's in artifacts, root folder, Ray model 9. And we'll click deploy. Once the deployment is completed, the status here should turn to green, and you will have access to the inference endpoint. At the same time, if we switch over to our OpenShift console and look into our test project, we now see that we have a model mesh running. So let's take the inference endpoint and test it out. We have the test model mesh endpoint function here. So we're gonna replace it with the URL and run the results. We'll scale it back, and this is the result. At the same time, we can also see that all our experiments were stored on the object store that we created, the data connection, and that we can also upload other information there if we want to, because it's available in our notebook, right? So the sequential model that was trained was uploaded under models folder. Now that we are satisfied with the setup, our training actually consists of two steps. One is to collect the data, prepare the data set, and do some feature engineering on it. So for that, we have this notebook over here. So that means that we would need to connect to Influx database, where we store all the time series data with the results of the load test, or you may also have that stored directly in a CSV file. And we can create a pipeline file programmatically, and you can fill in all the information, and then you can execute this in order to compile the pipeline. So in my case, I'm actually using the results that I used here previously as a data set, and I'm going to execute this script. So now the pipeline is compiled. We have the YAML that now we can use and deploy inside the pipelines. So here we're going to import pipeline. We can call it last test, and we can upload the pipeline. So uploading it first means that you need to download this to your local folder. So it's called mlast pipeline 3 YAML. Come back here, import the pipeline. So now we have the pipeline defined, the two steps here, and we can create a run. The run can be run immediately or schedule a recurring run. So we will run it immediately. Click create and the execution will start. The pipeline execution was successful and we can check on the results. I'm going to check the bucket contents once more. So we're going to run again the listing of the buckets and we see that we have now a new folder created here with, at the time the test was executed, with the model that was saved. This concludes our Hat OpenShift DataScience walkthrough and demo. I hope you enjoyed it.